So about 90% of our electrical energy is provided in the form of AC, and there are three good reasons for that. One, it's cheaper on the mega scale to produce it. Two, it's dead easy to transport along distances. And three, it's really easy to change the voltage up and down to a voltage that you might need. So we get most of our electrical energy in the AC format. Unfortunately, of course, different things need different formats. So if you've got an induction motor, you need AC. Some stuff doesn't care, things like ovens, kettles, toasters, filament lamps, AC or DC is just fine, and some things really need DC, like your television and your computer, that sort of thing. So transforming AC to DC was a huge problem, and of course there was a huge market for solving that problem because everybody has got an AC power supply in a huge part of the world, so the market's enormous. And that prompted a lot of work into how to go about doing this. Now, the first solutions were mechanical. When you're thinking about the rotary converter, the vibrating reed converter. Later, we got other solutions to it, things like the mercury lamp rectifier. None of those were particularly stable and none of them particularly good. And it wasn't until about 1920 or so when a certain kind of behaviour was noticed in copper and copper oxide, and it was very resistive one way and very non-resistive the other way. So if you hooked up a battery one way, you got nothing through. If you changed the battery around, it made no difference if that was there or not, and the copper oxide rectifier was born. Now, the copper oxide rectifier is something you see a lot on the internet. People take a copper plate and they heat it up on a blowtorch, or they heat it up on a cooker and knock off the black stuff, which is copper 2 oxide, and you're left with the red stuff, which is copper 1 oxide, and that's the stuff you want. Because copper oxide is a really interesting material. It doesn't only have rectification properties, it can also be used in a thermopile, as we've done in previous videos, and it can be used in photocells, which you see all over the place for homemade photocells, because it is a native P-type semiconductor. So you find it used a lot. Now, it was the first dry disc metallic rectifier. It was produced by Westinghouse. But of course the market was so huge, everybody else wasn't going to leave it at that state of affairs, and they came up with the selenium rectifier. Now, to make a copper oxide rectifier properly, what you need to do is bung your copper plate in a furnace for an hour or so, and then cool it down with a specific sequence, and then anneal it, and you get an oxide layer that binds well onto the copper plate. In home versions we don't do this, and that means it's a sensitive material. It knocks off really easy, it scratches really easy, it cracks and flakes off, so it's kind of difficult to use actually. In the industrial one, the process to stabilise it is difficult to replicate at home. And it's even worse with the selenium rectifier. The selenium rectifier is an aluminium or steel plate with a layer of bismuth over it, or nickel. Then over the top of that is some selenium. What they do then is put a layer of tin and cadmium alloy on top of that, and the cadmium reacts with the selenium to form cadmium selenide, and then the interface between the selenium and the selenide forms an NP junction, so it's a very early semiconductor. It came along a bit later in the day, and it did have a dominant place in the marketplace, but it wasn't able to handle as many amps as the copper oxide rectifier was. So until the advent of semiconductors, that was pretty much it. However, there is a little and lesser known third option. And that third option is the copper sulfur magnesium rectifier. This came along at the late stage of metal rectifiers when silicon rectifiers were coming in, and it did really well, surprisingly, but didn't have a chance to get an awful lot of recognition. Now, making one is really easy. It's not like your copper oxide version, and certainly not like the selenium version. What I've got here is some sulfur. You can buy this stuff in the garden stores. It's really easy to get hold of. And all we actually have to do is take a piece of copper wire and heat it up to glowing red. Once that's glowing red like that, stick it in your sulfur, pull it out, and the sulfur will burn a blue colour and create this metallic sheen over the copper wire. Be warned, it's burning sulfur, so it's a little stinky. I mean, a wire like that, nothing, but if you're going to do quite a few of them or a large plate, you probably want to be in a ventilated area or outside. Believe it or not, we have made our rectifier. All we have to do now is prove it's a rectifier. Okay, so as we can see this, I've got a power supply here that's giving me 12 volts AC, and I've connected up a strip of magnesium ribbon. It's just the magnesium ribbon you buy for showing how brightly it burns. And here's my piece of wire that I've put the sulfur just jiggling backwards and forwards slightly because it's being supplied with an AC current, so it can't do anything else. Now, however, if I touch my sulfur, and there we go. So the copper sulfide and magnesium is now forming a rectifier, and that motor can spin. So there we go, a really simple rectifier that is robust, easy, simple and cheap, and really didn't get much of a look in because it was just at that space of the end of selenium and the beginning of silicon, and it's sort of been forgotten along the path. But well worth investigating to see what else you might be able to do with that, because these metal rectifiers, remember, they can perform a whole load of different functions. So I thought I'd show you how to make that rectifier, what that rectifier was, in case anybody's interested in picking that up and seeing what else they can do with it. Anyway, I hope you enjoyed the video. Thank you very much for watching, and please remember to like and subscribe.